To achieve vehicle autonomy, a fusion of sensor technologies is required to give a complete picture of the environment in a variety of situations. Radar performs coarse mapping at medium to long range, but lacks the fine resolution required for object identification. Cameras can read road signs and view colour, but are limited by the visibility conditions. Ultrasound is limited to short-range manoeuvring, such as parking assist. LiDAR is a technique that can provide 360-degree high-resolution mapping at short to long range. The challenge for LiDAR is to work in harsh environments and with low reflective targets at long range. A LiDAR system measures the distance to an object using laser light. The laser fires a short pulse of light which is reflected back to the sensor by objects within the system's field of view. The sensor precisely measures the travel time of the returned laser pulse. This so-called time of flight is converted to a distance using the relation between the speed of light, the distance travelled, and the time taken. Distance calculation can be made using either a single laser pulse per measurement or multiple laser pulses per measurement. Let's look at the single shot method first. When the laser emits the pulse, it starts a timer that is stopped upon detection of the returned laser light. This measured time of flight is then used to calculate the distance to the reflecting object. However, the LiDAR measurement is complicated by the real-world conditions. The system must be able to cope with harsh environments and with low reflectivity targets at long range. A harsh environment is any external factor that might interfere with the LiDAR measurement. One example is bright sunlight, which exposes the sensor to a high level of ambient light. It forms a background signal that can interfere with the detection of the laser pulse and potentially saturate the sensor. Methods to reduce the amount of detected sunlight are employed to address this. One method is the use of a narrow bandpass filter, which only accepts wavelengths close to that of the laser light. A second method is to restrict the angle of view. Both of these methods reduce the amount of ambient light reaching the sensor, improving the dynamic range and allowing weaker return signals to be detected. The second real-world challenge relates to the target object's reflectivity. This determines how much light gets returned back to the sensor. Some materials, such as retroreflectors, reflect all of the incident light back in the same direction. In this case, the returned laser pulse is extremely bright. The most challenging situation is that of a low reflectivity target, such as a tyre, which only diffusely reflects about 5% of the laser light. Such objects result in a very faint return pulse. The return signal from low reflectivity objects can be increased by sending out a more powerful laser pulse. In practice, the total laser power a LiDAR can use is restricted by eye safety requirements, so a brighter laser must be used with shorter duration pulses to keep the overall power within safe limits. The third real-world challenge is that of ranging to distant objects. As the distance increases, the return signal gets weaker, while the level of detected background light stays more or less constant. The ability to range at greater distances is largely determined by the sensor's ability to detect weak signals. The SensL silicon photomultiplier is capable of detecting low light signals down to the level of a single photon, due to its high gain and low noise. This allows it to range to greater distances than other sensor types. A LiDAR system can be optimized for the real-world environment by reducing background light, and distant, low-reflective objects can be seen when a fast, bright laser pulse is used in conjunction with a silicon photomultiplier. However, there comes a point at long range where the return signal is so faint that it is reduced to just single photons. The signal is no longer distinguishable from the background light, and in this situation, single-shot LiDAR cannot work. To extend the range further, a technique can be used to identify correlated photons. This is achieved with the use of a single photon-sensitive sensor in combination with a multi-shot technique that combines many time-of-flight measurements for each distance calculation. Only a SensL silicon photomultiplier, or SPAD array, combines the ability to detect single photons with the practical requirements necessary for automotive applications. To identify the photons that are correlated in time, the sensor makes a time-of-flight measurement whenever a photon is detected. Sometimes the detected photon is from the ambient background light, and sometimes it is from the returned laser pulse. The sensor has no way of distinguishing whether the photon's origin is sunlight or from the returned laser light. Therefore, reliable ranging information cannot be obtained from any single measurement. Instead, the system continues to make time-of-flight measurements using many laser pulses and adds each measurement to a distribution plot. As more time-of-flight values are added, a peak can be seen to form above the background. This peak is made up of the photons that were correlated with the laser pulse. The time-of-flight value that corresponds to the peak center is then used to calculate the distance. In practice, the histogram looks like this. The correlated photons associated with a distance of 100 meters form a clear peak, and the uncorrelated photons create a noise floor. To recap, conventional time-of-flight LiDAR uses a single laser pulse per distance measurement, but is limited to short to medium range applications or high reflectivity targets. Multi-shot LiDAR uses multiple laser pulses to get a single distance measurement by identifying correlated photons. This technique has the benefit of working at both long distance and with low reflectivity targets. The multi-shot approach also addresses other harsh environment challenges such as rain, and potential confusion with laser pulses emitted from other vehicles on the road. To create a full picture of the environment, the system needs more than a single point measurement. Sensil has developed a 16-element linear array of silicon photomultipliers. This is used with 16 separate laser beams, which fan out vertically to simultaneously sample a number of points in the field of view. This fan of 16 points is then scanned horizontally to give a point cloud of distance measurements across the field of view and build up a three-dimensional model of the scene. The SensL silicon photomultiplier array is just one part of the LiDAR system that comprises the laser, beam steering, collection optics, the sensor array, and processing electronics. Multiple systems can be mounted onto a vehicle to provide long-range 360-degree mapping in a variety of real-world conditions. Sensil, the sensor for long-range solid-state LiDAR in the real world.